Now let's talk about one-hot encoding. When is one-hot encoding used? It's used when we have qualitative data that we want to incorporate into our model to improve the model's explanatory power. But normally, we can't include qualitative data in a model. One-hot encoding converts this qualitative data into a collection of dummy variables that take on only the values 0 and 1. Since dummy variables are examples of quantitative data, we can then use those dummy variables in our model. Let's look at an example of one-hot encoding. Alright, let's look at our example here. We have here a column of qualitative data labeled type. Type takes on three possible values, or three possible categories, A, B, and C. Therefore, I have used three dummy variables, also labeled A, B, and C. Let's look at the first row of type. The value there is A. Therefore, I'm going to put a 1 in the A column and zeros in the B and C columns in the first row. I'm going to do this for every row where there is an A. Now, in every row where there's a B, I will put a 1 only in the B column, and for every row where there is a C, I will put a 1 only in the C column, and leave the rest of the columns as zeros. You can see that as I'm going row by row, I'm switching on the column that corresponds to the category that I'm trying to encode. In each row of my dummy variable matrix, you can see that there is only one 1. There's only one hot value. Therefore, this method is known as one-hot encoding. Now, let's look at it using a column approach. Alright, now let's go column by column. Here I've copied over our type column from before with the same qualitative values, and also the design matrix that we derived before. It's over here. Let's call the first column of the design matrix the vector xa, the second column the vector xb, and the third column the vector xc. Basically, the column vector x sub k is the values of the dummy variable k. That is, for instance, the vector x sub a is the values of the dummy variable a, and so on. We see that if we pick an arbitrary row I of one of these columns, as we did before, that the ith value of the column vector xk is 1 if the ith observation has the value k and 0 otherwise. For example, the first row and the first element of the column vector xa is 1 because the first observation has value a. But if we look at that same column and we look at the last value, it's 0 because the last observation has value c. It does not have value a. Correspondingly, the last value in the vector x sub c is 1 because the last observation has value c. Keep in mind this mathematical representation of the design matrix because we will be using it to derive some important results later in the discussion worksheet. Now let's look at discussion problem number 7. I've copied over the design matrix from before. Let's call it x. We wish to show that the columns of x are orthogonal. That is, for any two arbitrary column vectors x sub j and x sub k, for j not equal to k, we wish to show that the dot product of x sub j and x sub k is 0. So let's write out the definition of the dot product here and look at the product inside the summation. By simply looking at the design matrix, we can see that this product is always going to be either 0 times 0, 1 times 0, or 0 times 1. But it can never be 1 times 1. Why is that? Because this is one-hot encoding. If we know that one of the values in the ith row is 1, we automatically know that the rest of the values in that row are 0. That is, if x sub j comma I is 1, we automatically know that x sub k comma I is 0, and vice versa. Therefore, every term in the summation, every product here will be equal to 0, and the entire summation is also equal to 0. Thus, the dot product x sub j times x sub k will be 0, whatever one of these three columns that we're choosing. And therefore, the columns of x are orthogonal, QED. Okay, let's do problem 8 on the discussion worksheet. Here I've copied over the design matrix X again, and as we know, we can write it in this form with the column vectors x sub A, x sub B, and x sub C. I've also taken the transpose of the matrix, and that can be written in this way where, again, I just take the column vectors and turn them into row vectors. What happens when I take the matrix product of x transpose and x? Well, it turns out that x transpose x is a square diagonal matrix, and the elements in the diagonal are 4, 3, and 3. What a coincidence! There are 4 non-zero values in the first column, 3 non-zero values in the second column, and 3 non-zero values in the third column of x. Is this a coincidence? Well, let's try and prove this mathematically. Here, I've written out the result of the matrix product x transpose x by looking at each of the individual column vectors. Well, this looks like a total mess, but remember what we proved before. We proved that the dot product of x sub j and x sub k is 0 for all j that is not equal to k. And I know that a dot product can be rewritten using a transpose like this. So when we look at this matrix product, every element of this matrix where the subscripts don't match is 0 because of orthogonality. And therefore, this simply simplifies to this. Basically, we can see that all of the values where the subscripts don't match, they become 0. Well, how did I get the values on the diagonal? N sub A, N sub B, and N sub C. Well, what do I denote by that? N sub A is the count of the number of observations that were A, N sub B is the count of the number of observations that were B, and N sub C is the count of the number of observations that were C. In our example, that was 4, 3, and 3, respectively. Well, let me take a look at each of the diagonal elements of this matrix product. What happens when we take the dot product of the column vector x sub A with itself? That's what it means to have x sub A transpose times x sub A. Well, let's go look at our example design matrix X. If I take the dot product with itself, I only have 4 non-zero elements because there were 4 A's in my original column vector. So the result of that dot product will be 4 times 1 times 1, so 4 times 1, which is 4, which is exactly the number of A observations I had. Similarly, if I take the product of a dot product of x sub B with itself, I will get 3, because in my summation there will only be 3 non-zero terms, and those terms will all be 1. So I will get 3, which is the number of B observations I had. And finally, this value is also going to be the number of C observations which I had, which is 3. And so we can see how we get from here to here. And so x transpose times x is equivalent to this, which is consistent with our example and exactly what we wanted to prove. QED. All right, time to do question number 9. There is nothing new here except for our vector y. What happens when I take the product x transpose times the vector y? Well, as before, I can write out the individual elements using my definition over here, and I can figure out what each of these becomes. Let's look specifically at the dot product of the column vector x sub A and my vector y. We see that since the only non-zero values in the column vector x sub A are at the top, we will only pick out the first 4 values in my y vector. That means I'm picking out y sub I such that the ith row corresponds to a value in my original qualitative vector that was an observation of A. That's what this notation means. I'm picking out the values of y in the rows where I originally had an A. Similarly, what happens when I take x sub B transpose times y, which is the dot product of x sub B and y, I'm going to only pick out the values of my y vector where I originally had a B. And finally, when I take the dot product of x sub C and y, I'm only going to pick out the values of y where I originally had a C. This is exactly what I've written down here. In generally, when I take the dot product of x sub k and y, I'm picking out the values of y where originally I had k as an observation. And that exactly gives us the equivalence between this, and proves that x transpose times y is also equal to this. QED. Okay, question 10 on the worksheet. We're in the end game now, and correspondingly, I've done an ambitious crossover in which I've brought over all of our important results from the previous parts on one-hot encoding. We have a result for x transpose x, and we have a result for x transpose times our vector of labels y. Here I've also written down the inverse of x transpose x. Since this is a diagonal matrix, we can actually just find the inverse by taking the inverse of each of the diagonal elements. And you can confirm for yourself really quickly that if you multiply these two matrices, that you'll get the identity matrix. Now that we have all of our results, we can solve for our optimal vector of weights beta that will allow us to predict our given labels y. And we know that we have a normal equation that allows us to solve for this vector of weights beta. From x beta equals y, we got this normal equation, which is beta is equal to the inverse of x transpose x times the inverse times the transpose of x times y. And we can plug in for our two results here, and it gives us this, and you can do the matrix multiplication, and we end up with this result. Now, what is this? What is this telling us? Well, this looks very much like an average, and indeed it is an average. It's the average of all of the elements of the vector y where we originally had an observation A. It's the average of those corresponding labels. This is also the average, the second element is the average of the elements of y where we originally had a B, and the last element is the average of all the values of y where we originally had a C. And so our optimal vector of weights beta is actually just the average of the corresponding labels for each different type of observation that we had. And you know I like to say QED, and I'm going to say it again, QED. That's exactly what we wanted to show. But in all seriousness, if you have to take away one thing from this entire exercise, it is that the optimal weights, the fitted coefficients for each of our values for our dummy variable x sub a, x sub b, and x sub c are simply going to be the averages of the corresponding labels that we were given, y bar sub a, y bar sub b, and y bar sub c.